Okay, let's unpack this. For, gosh, more than half a century, silicon hasn't just been a foundation, it's been the foundation of modern tech.
Absolutely. It dictates really the physics of our digital world. Speed, size.
Yeah, everything from the tiniest chip in your watch
Hmm.
right up to these massive server farms running the cloud. It's all built on silicon field effect transistors, FETs.
Hmm.
But what happens when, the king hits a wall, a hard physical limit? It just can't shrink past.
And that is precisely the question, isn't it? That's what launched this whole deep dive. We're looking at this pretty major breakthrough from Penn State
A
researchers.
team led by Saptarshi Das, you mentioned.
That's right. And they think they've found the way forward beyond silicon. Their announcement, it's genuinely seismic. They've unveiled what they've validated as the world's first fully functional silicon-free computer.
Wow. Okay, so that's our mission today then, listener. We need to get past the theory into the actual engineering reality here.
Yeah, we need to understand what exactly is this crisis facing silicon. What materials did they actually use to replace it?
And how did they build this silicon-free architecture? Because that's essential, right, for these future ultra-small, ultra-efficient electronics. How is it actually built and, crucially, scaled up for the first time?
Well, to really appreciate just how big a deal this is, we have to start with silicon itself, its dominance over decades.
It really is the defining material for semiconductors.
Completely. You know, that exponential progress we talk about, Moore's law, the doubling of transistors on a chip every couple of years,
Yeah, the relentless shrinking.
that has relied entirely on our ability to just keep making silicon transistors smaller and smaller.
And the idea was always, smaller transistor means faster, more efficient computer, at least in theory.
Yeah,
But we've been hearing for years now, haven't we, that we're hitting these fundamental physical walls.
we really are.
So what exactly is the technical crisis that Das and his team were trying to solve? What happens when silicon gets too small?
It really boils down to physics, fundamental physics at the atomic scale. Saptarshi Das, the lead researcher, he highlighted this. When you keep forcing silicon devices to shrink, especially that crucial dimension, the gate length,
Right.
the performance doesn't just stop improving, it actually starts to degrade. It gets worse because of inherent leakage issues.
Ah, leakage. And for listeners who follow this stuff, we're talking about things like short channel effects starting to really take over.
Precisely. Short channel effects, that's when the channel length, the path the electrons take, becomes so short it's comparable to the depletion layer width. Basically, the electrical isolation breaks down.
So the gate, the part that's supposed to control the current flow, it loses control. The source and drain terminals start messing with each other directly.
Exactly. And the really killer consequence of shrinking things down this much is something called quantum tunneling leakage.
Okay, quantum tunneling. Sounds exotic.
It kind of is. At these tiny thicknesses, we're talking just a few nanometers, maybe single digits, electrons just stop playing by the classical physics rulebook.
They don't behave like little billiard balls anymore.
Not at all. They can literally tunnel through the insulating barriers that are supposed to block them,
Even when the transistor is off.
especially when it's off. That leads to massive power drain, even when the chip is just sitting idle doing nothing. Standby power consumption goes through the roof, and all that leakage generates heat.
So you can make the transistor physically smaller, but you pay a huge price in efficiency and thermal stability. Silicon just hits this point where its fundamental properties can't hold up at that near atomic thickness.
It hits a wall, a physical wall.
Okay, so if shrinking silicon is the problem, the Penn State team's solution sounds pretty radical. Just abandon silicon altogether, move to materials that are already atomically thin.
That's the core idea. Shift from a 3D bulk material, silicon, to these two-dimensional or 2D materials. Things that exist naturally at just an atom or a few atoms thick.
Like graphene and its relatives.
Exactly. Materials like graphene, or the ones they used here, transition metal dichalcogenides. What's fascinating, and the key scientific advantage, is that these 2D substances are, well, already basically one atom thick by definition.
So they don't need to be shrunk down to that level.
Right. And crucially, they maintain their excellent electronic properties, things like having a good band gap, which silicon struggles with when it gets too thin, even at that extreme single atom scale.
They're sort of naturally immune to some of those short channel effects that plague tiny silicon transistors.
To a large extent, yes. Their structure inherently confines the electron flow to a plane, which helps maintain control.
And the milestone here, you said, it's huge because this isn't just some lab curiosity about a material property.
No, not at all. This is a massive engineering feat. They've built a fully functional computer, something that performs logic operations, carries out basic instructions.
And it's built entirely from these 2D materials, a complete architectural break from silicon.
That's the achievement.
Okay, let's dig into that architecture then. When we talk about a modern computer, especially one aiming for low power and high efficiency, we're almost always talking about CMOS technology, right?
That's spot on. CMOS, complementary metal oxide semiconductor. It is the essential blueprint, the core technology in pretty much every modern electronic device you can think of.
Why CMOS? What makes it so dominant?
Because it offers this almost perfect marriage of high performance when it's active and incredibly low static power consumption when it's idle.
And the key is that word complementary.
Exactly. Complementary. It means you absolutely must have two different reliable types of semiconductors working together in perfect harmony.
Okay, what are those two types?
You need N-type transistors and P-type transistors. N-type FETs use negative charge carriers, electrons, to conduct current from the source to the drain.
Got it. Electrons. Negative. N-type.
And P-type FETs use positive charge carriers, which we call holes, basically the absence of an electron, to conduct current.
Positive. P-type. Makes sense.
And they work together in pairs. In any stable logic state, whether it's representing a digital 1 or a 0, only one of those two complementary transistors, the N-type or the P-type, is actually on and allowing significant current to flow. The other is off.
Ah, so it minimizes leakage. When the circuit element is just holding a state, not actively switching, there's very little power being wasted.
Precisely. That's what enables the extremely low standby power that makes, your phone battery last all day, or allows massive data centers to operate without melting down.
But creating this perfectly matched complementary pair, that's been the big stumbling block for other materials trying to replace silicon, hasn't it?
Absolutely. That's been the Achilles heel for years.
Mm-hmm.
Silicon, it turns out, is naturally quite ambipolar.
Ambipolar, meaning
Then with some clever processing doping, you can reliably create both N-type and P-type regions within the same silicon crystal. It handles both roles reasonably well.
Okay, so silicon is versatile, but when you move to these new 2D materials,
you hit a massive engineering challenge, especially with achieving reliable P-doping. Most of these promising 2D semiconductors, particularly the family called transition metal dichalcogenides, or TMDs.
MOS2 and WSE2 we'll get to.
Exactly those. They tend to be intrinsically N-type. It's just their natural electronic state.
So making a great N-type transistor out of a 2D material is relatively easy, or at least easier.
Comparatively, yes. But creating an equally good, stable, high-performing P-type transistor, the essential complementary partner, that's been incredibly difficult.
What happens? Do they just not perform well, or are they unstable?
Often both. You might get low performance, low mobility for the holes, or the doping process introduces a ton of defects, or the P-type behavior isn't stable over time. It just hasn't worked reliably enough to build complex circuits.
And that has been the biggest barrier stopping someone from building a fully 2D CMOS computer until now.
Precisely. Substarchi Das pointed this out too. Previous studies, sure, they demonstrated maybe a few 2D transistors working together in a simple logic gate, a small circuit.
Little building blocks.
Right. But scaling that up, getting that successful complementary N-type and P-type relationship to work reliably across thousands, maybe millions of transistors needed for a real computer, that remained elusive until this project.
Their success really hinges on finding the right pair of 2D materials that can be reliably made in large quantities.
Exactly, and fabricated consistently.
Okay, so let's get back to the fundamental component, the field effect transistor, the FET. We know silicon FETs run into trouble with leakage when they get too small.
Right, the quantum tunneling kills them.
So the 2D materials offer a fresh start. What specific materials did this Penn State team choose to replace silicon in those two essential transistor roles, the N-type and the P-type?
So they moved away from using just one material, like silicon, to using a specialized duo. They picked two distinct 2D materials, known for having really good electronic properties on their own.
Okay, material number one for the N-type.
For the crucial N-type transistors, the ones carrying the negative electron current, they used molybdenum disulfide, usually written as MS2.
MOS2. Okay, I've definitely seen that one pop up a lot in research papers. Often talked about as maybe the successor to graphene for electronics, because it actually has a band gap.
That's a big reason why. MOS2 is excellent for N-type operation. It has that natural N-type tendency we talked about, and it has a very useful band gap, around 1.8 electron volts in its single-layer form.
Which is high enough to switch it off properly, reducing that leakage current compared to graphene, which has no band gap.
Exactly. It gives them the potential for both good speed and a really good on-off ratio, which is critical for low power.
All right, so MS2 handles the N-type. Now for the really tricky part, the P-type, the complementary piece that unlocks CMOS, what did they use there?
That critical role was filled by tungsten diselenide, or WSE2.
WSC2, okay, another TMD. Why that one for P-type?
Well, the researchers found that WSE2 could be more reliably coaxed into exhibiting good P-type behavior. It seems to require maybe less harsh processing or modification compared to trying to force MOS2 to be P-type.
So it naturally lends itself better to conducting those positive holes.
It seems so, or at least it's easier to get good hole mobility out of it without creating too many problems. So by combining MOS2 specifically for the N-type function and WSC2 specifically for the P-type function,
They solved that fundamental N-type mismatch problem that had basically stalled the field for a decade.
that's the core materials innovation right
It
there.
really is a fundamental shift. You're not just swapping silicon for a 2D material. You're replacing one versatile material, silicon, with two specialized atomic layer materials, OS2 and WSE2, each chosen because it performs one of the complementary functions better at this extreme nanometer scale.
A tailored approach.
I did like that conceptual illustration they provided in the sources, showing a keyboard with some keys labeled MOS2 and others WSE2.
Yeah, it was a nice touch.
It really hits home that these two specific materials are now, symbolically at least, the new atomic foundation for this type of computing.
And when we move from just picking the materials to actually making something with them, the achievement gets even clearer. The real significance isn't just, oh, we use MOS2 and WSE2. It's the massive, successful engineering effort in actually scaling up the fabrication.
Right. Do some self-emphasize this. Going from that tiny, maybe handcrafted lab circuit with a few transistors
To a complex, functional computer, a system with thousands of components all working together. That had been the major roadblock for the whole industry.
it's that classic jump from a scientific proof of concept to a genuine engineering prototype that could, potentially be manufactured.
And they made that jump. They didn't just build some tiny demo device in a corner of a chip. They successfully manufactured a CMOS computer entirely from large area grown molybdenum disulfide and tungsten diselenide.
Large area grown, that's key, meaning they had to figure out how to grow big, essentially perfect sheets of both these atomic materials.
Exactly. Expansive sheets, virtually flawless, and then figure out how to stack them, pattern them, connect them, all with atomic level precision.
That sounds incredibly difficult.
Yeah.
It implies they needed a fabrication method that could produce these sheets uniformly over a large area and potentially in high volume. What specific technique did they use for that?
They used a method that's actually a favorite in industry for large-scale production of thin films, but they specifically adapted it for these ultra-thin 2D layers. It's called metal organic chemical vapor deposition, or MOCVD.
MOCVD. Okay, sounds a bit intimidating. Can we break that down simply for the listener? How does MOCVD actually create these big atomically thin sheets so uniformly?
Yeah, you can think of it almost like atomic scale spray painting, but under extremely controlled conditions inside a reactor chamber.
Okay, atomic spray painting. I like that.
You start by vaporizing the chemical ingredients you need. These are called metal organic precursors.
Yeah.
They contain the molybdenum or tungsten and the sulfur or selenium.
Got it. The basic building blocks in gas form.
Right. Then you flow these precursor gases over a heated substrate, maybe a wafer of silicon dioxide or sapphire. The heat provides the energy to force a chemical reaction right at the surface.
And the reaction product, the MOS2 and the WSE2, gets deposited onto that surface.
Exactly. It deposits onto the substrate, ideally just one atomic layer at a time. The big advantage of MOCVD, and why industry likes it, is that it's highly scalable. You can do this over large wafers, and it generally provides much better film uniformity across that large area compared to older methods like, say, taking sticky tape to a crystal and peeling off flakes.
The Scotch tape method that won the Nobel for graphene, great for discovery, not so great for mass production.
Precisely. You need uniformity for manufacturing. If you have even a tiny defect, maybe a missing atom or a slightly thicker patch in one area of your sheet.
That transistor built on that spot, might not work right. Or it
Yeah.
might work differently from the one next to it.
Exactly. And if you're trying to build a chip with thousands or millions or billions of transistors, that kind of variation, that lack of uniformity, it kills your yield. You end up with too many faulty chips.
So the MOCVD process had to be absolutely dialed in. And the scale they achieved here is pretty impressive, isn't it?
It really is. Using this MOCVD process, the team managed to fabricate over 1,000 of each type of transistor. So more than 1,000 N-type MOS2 FETs and more than 1,000 P-type WSE2 FETs, all integrated together.
Wow, over 2,000 transistors total in this first computer. That density, that scale, that's what starts to make it look industrially viable, doesn't it? Not just a lab experiment anymore.
Absolutely. It demonstrates the potential for manufacturability.
But, okay, fabricating 2,000 plus transistors is one thing. Getting them all to work together perfectly in that CMOS structure like a synchronized army, that's another challenge entirely. The sources mentioned they had to carefully adjust the device fabrication and, importantly, the post-processing steps. What specific technical problem were they fine-tuning there?
The absolutely critical technical task was tuning the threshold voltages of both the N-type MOS2 transistors and the P-type WSE2 transistors.
Okay, threshold voltage, let's remind the listener. That's basically the on-switch voltage, right? The minimum voltage you need to apply to the gate to actually turn the transistor on and let current flow.
Exactly. It's the point where the channel opens up.
So why is tuning this so incredibly vital for their complementary MOS2 WSE2 system? Why can't they just use them as they come out of the MOCVD?
Because for CMOS logic to work correctly and efficiently, the threshold voltage of the NFT and the threshold voltage of its PFE partner have to be precisely matched. They need to be sort of symmetrical around a certain point relative to the overall power supply voltage.
What happens if they're not matched?
If the voltages are off, then one transistor might turn on too early or the other might turn off too late as the input signal switches. This overlap where both might be partially on, even for a moment.
Leads to massive power leakage during switching. Or just unreliable logic states.
Both. You get huge dynamic power consumption, and the logic gates might not produce clean 0 or 1 outputs. The whole circuit becomes unreliable and power hungry.
So how do they actually tune these threshold voltages on an atomic scale?
It often involves really advanced techniques, things like work function engineering. That means carefully choosing the materials used for the gate electrode itself, or perhaps modifying the thin insulating dielectric layer right next to the 2D material.
But changing the materials right around the channel affects the electric field just enough to shift that on-switch voltage point.
Precisely. You're subtly adjusting the energy levels, the band alignments at those critical interfaces. It's using materials science and interface physics to precisely dial in the electrical behavior of these two different atomic materials, MS2 and WSE2, so they behave as perfect complementary partners.
That sounds incredibly delicate, getting that chemistry and physics just right so they snap into that ideal CMOS behavior.
It really is the crucial gap bridging step. That careful adjustment, that fine-tuning, is what ensured their MOS2 and WSE2 transistors could reliably combine to create fully functional CMOS logic circuits. It shows a level of control over the interfaces between these 2D layers that, frankly, hadn't been demonstrated before at this scale. Previous attempts really struggled with high variability between devices.
That makes sense. And speaking of variability, how did they manage potential cross-contamination? You're growing MOS2, you're growing WSE2. Probably the same fabrication facility, maybe even sequentially on the same wafer.
That's a huge challenge.
The risk of getting a bit of sulfur where you want selenium, or vice versa, or just defects forming at the boundary where you pattern one next to the other, that must be significant, right? And wouldn't that directly mess up the device performance and increase that variability you mentioned?
Absolutely. That is exactly the kind of practical fabrication problem that separates success from failure at this scale. Device variability, those tiny, unwanted differences in performance between transistors that are supposed to be identical, is the absolute enemy of large-scale integration, like building a whole computer.
So the fact that they did succeed,
Yeah.
building over 1,000 of each type that worked well enough together,
It strongly suggests they developed an exceptionally clean and well-controlled fabrication sequence. They must have figured out really good ways to pattern and etch these materials precisely, maybe using protective layers or perhaps growing the large sheets of MOS2 and WSE2 separately first, and then using some kind of advanced layer transfer technique to stack them together cleanly.
interesting. So maybe not growing them directly next to each other, but stacking pre-grown sheets.
That's one possibility that can minimize cross-contamination. Whatever the exact method, this dedication to clean, scalable fabrication, to minimizing that device-to-device variability, that's really the hidden key. That's what allowed them to get past that 1,000 transistor benchmark and actually achieve working logic circuits on a computer scale. Without tackling variability, you'd be stuck at the level of just a few dozen transistors max.
All right, so they've got the right materials, MOS2 and WSC2. They've figured out how to grow them uniformly using MOCVD. They've scaled it up to over 2,000 transistors. And they've fine-tuned the threshold voltages for proper CMOS operation. The architecture is validated. The fabrication hurdles seem to be overcome, at least for the scale. Let's look at the device itself. They built a functional prototype computer. What does it actually do? What's its performance profile like?
Okay, so the device itself, they refer to it as a one instruction set computer.
One instruction set computer, OISC, sometimes called, meaning it's extremely simple, designed to execute just one specific, very basic instruction.
Exactly. It's a common architecture for early-stage research or highly specialized tasks because it simplifies the design enormously. You prove the core logic works without needing complex instruction decoding. The first author on the paper, Sibir Ghosh, provided the key operational detail.
And what did he report? How does it perform?
Well, the really good news is on the power front.
Yeah.
Ghosh highlighted that it operates at very low supply voltages.
Lower voltage usually means lower power.
Right. And it exhibits minimal power consumption overall. That's a direct payoff from getting that 2D CMOS integration right, minimizing that static leakage we talked about.
Okay, low power is fantastic. That's a huge driver for moving beyond silicon, especially for mobile devices, wearables, IoT sensors, anywhere battery life and heat are critical concerns.
Absolutely paramount.
But what about speed? How fast can this first-generation silicon-free machine actually run?
So Ghosh was quite open and candid about the current speed limitations. The prototype operates at frequencies up to 25 kilohertz.
25 kilohertz. Okay, let's definitely put that number in context for everyone listening.
Yeah, it needs context.
A typical processor in your laptop or smartphone today runs in the gigahertz range, right? Billions of cycles per second.
Usually multiple gigahertz, yeah. 2, 3, 4 gigahertz is common.
And 25 kilohertz is 25,000 cycles per second.
That's right.
So we're talking orders of magnitude slower, maybe 5 orders of magnitude, something like 100,000 times slower than a current silicon chip.
It is objectively incredibly slow compared to today's silicon CMOS standard. And Ghosh acknowledged that. It's important context. However,
There's always a however in research.
there is. Ghosh emphasized, and I think this is crucial, the primary goal of this first prototype wasn't raw speed. It was validation. Validation of the entire integrated system.
Proving that it could actually work at all as a computer.
Exactly. The fact that this machine, built entirely from MOSO2 and WSE2, can successfully perform simple logic operations, that it can actually fetch and execute instructions reliably, even if slowly, that validates the entire materials platform. It confirms that this complementary MOSO2 WSE2 pairing is a viable foundation, a real building block for the next generation of electronics.
It really does remind me of the very early days of silicon integrated circuits back in the, late 50s, early 60s? Those first chips were also incredibly slow and could only do very simple things.
Absolutely analogous. The breakthrough then wasn't beating the existing vacuum tube computers on speed immediately. It was proving that you could integrate multiple transistors onto a single piece of silicon reliably. That integration was the revolution.
So the low speed here, the 25 kilohertz, it's not an inherent fundamental limit of the 2D materials themselves.
Not necessarily, no. It more likely points to areas that just need optimization. Things like the interconnects, the tiny wires connecting the transistors. Maybe they're too resistive or have high capacitance right now. Or the device geometry itself isn't optimized for speed yet. Material purity could probably be improved further.
So the classic engineering challenges you face whenever you scale up a brand new technology. The basic foundation works. Now you need years of refinement to make it fast.
Exactly. The foundation seems solid. The potential is there.
And what's really impressive and shows they're thinking long-term is that the researchers didn't just stop at building and testing the prototype. They immediately went on to develop a sophisticated computational model.
Yeah, this is where you see the really rigorous scientific approach going beyond just the experiment. They built this detailed computational model, and crucially, they calibrated it using all the real experimental data they gathered from their thousands of fabricated transistors.
So it's grounded in reality. And they even included the imperfections.
Yes, very important. They specifically incorporated the observed device variations, the fact that not every transistor was perfectly identical, and the likely presence of some defects that inevitably occur when you're building over 2,000 atomic scale devices.
Okay, so this model isn't just some idealized, perfect world simulation. It's based on the actual, slightly messy reality of their current fabrication process. What was the main point of building such a detailed model? What were they trying to figure out?
It really served two main purposes, as I see it. First, it allows them to project the potential performance of future, more optimized versions of their 2D CMOS computers. What happens when they manage to clean up the fabrication further, reduce that variability, tweak the transistor shapes for speed?
So predicting the roadmap.
Predicting the roadmap, exactly. And second, and perhaps most importantly for justifying further research, the model allows them to benchmark that projected future performance against where state-of-the-art silicon technology is right now and where it's likely to go in the near future.
So they can start to answer the question, can this 2D platform eventually beat silicon, or at least compete with it once it's mature?
That's the billion-dollar question, isn't it? And what did the model suggest? What was the conclusion from Sue Birgosh and the team based on these projections?
Yeah, what did they find?
Their conclusion was essentially that while, yes, significant optimization is definitely still needed, they're very clear it's still early days, first-generation stuff.
No surprise there.
The inherent scaling advantages of using these atomically thin 2D materials suggest that future optimized 2D chips could be significantly more energy efficient than even the most advanced silicon nodes we have today. And potentially, they could scale to even higher transistor densities because you're not fighting those same short channel effects as aggressively.
So the potential is there, according to the physics baked into the model.
Exactly. It marks, they argue, a really significant milestone in pushing electronics forward using 2D materials because it doesn't just show a working device, it provides a quantitative, physics-based roadmap showing the path from this initial 25 kilohertz prototype towards potentially competitive speeds and superior efficiency. The experiment established the structural integrity, you could say, and the modeling established the immense future potential.
That really puts the 25 kilohertz figure in perspective then. It's a starting point, not the end point.
Precisely. Now, it's also really important, I think, to put this whole achievement into its proper historical context. Because when a paper like this drops, especially in a high-profile journal like Nature, this was published in June 2025, remember, it can feel like this sudden overnight revolution.
Yeah, it seems to come out of nowhere.
But Saptarshi Das offered a really crucial comparison of the development timelines involved here, and that comparison really helps contextualize just how fast this 2D materials field is actually moving.
Okay, let's look at those timelines again. Silicon first.
Silicon technology. You start from, say, the invention of the point contact transistor at Bell Labs in the late 1940s.
Right. Bardeen, Bratton, Shockley.
Through decades upon decades of painstaking refinement, industrial scaling, commercialization, silicon has been under intense focused development for approximately 80 years. 80.
80 years, wow. Generations of scientists and engineers, trillions of dollars probably invested globally over that time to get us to the chips we have today.
An absolutely enormous sustained effort. Now, compare that to the 2D materials platform they're using. Graphene, okay, that was first isolated and characterized back in 2004.
The Nobel Prize work.
Right. But the really serious focused research into using 2D materials as a platform for scalable electronic devices, particularly looking beyond graphene to these semiconducting TMDs like MOS2 and WSE2 that have band gaps, that research effort only really kicked into high gear around 2010.
So maybe 15 years ago, give or take.
Roughly, yeah. Maybe 15 years of really intensive work specifically aimed at building electronics with these things.
Okay, 80 years for silicon to reach its current state versus about 15 years for 2D materials.
And in that roughly 15 years, this Penn State team has gone from, basic physics concepts and early material synthesis to building this functioning, scaled-up, silicon-free computer prototype.
When you put it like that.
Des rightly called it a major leap forward. The pace of progress is dramatically faster than the early days of silicon.
That acceleration is just staggering, isn't it? It's not just that scientists today are necessarily smarter, is it? It must be that the whole environment, the infrastructure for doing this kind of research has completely changed.
That's a huge part of it. Think about it. When silicon research was starting out in the 40s and 50s, they had to invent everything from scratch.
Like how to purify silicon to incredible levels, how to grow perfect crystals, how to do photolithography to pattern things, even how to build the clean rooms needed to avoid contamination.
Exactly. They had to invent the tools while they were inventing the technology. Whereas the researchers working on 2D materials today, well, they're standing on the shoulders of giants, aren't they?
They inherit 80 years of accumulated knowledge from the silicon industry.
Immensely so. They benefit hugely from all that existing semiconductor know-how regarding things like lithography, etching techniques, thin film deposition methods like MOCVD, which they then adapt and refine for these new atomic materials. They don't have to reinvent the wheel entirely. They just need to figure out how to make a wheel out of MOS2 and WSE2 instead of silicon.
And the tools available today must be vastly better, too, for actually seeing and analyzing these materials.
Oh, absolutely. The availability of incredibly powerful characterization tools that simply didn't exist 50 or 60 years ago. Things like high-resolution transmission electron microscopes, TAM, or atomic force microscopes, AFM.
Tools that let them literally image the atomic lattice, see individual defects, measure the thickness layer by layer.
Right. They can get almost instantaneous feedback on their material quality and device structure at the atomic scale. Early silicon pioneers could only dream of that kind of analytical power. It allows for much faster cycles of experimentation and refinement.
So, the incredible speed of progress we're seeing here reflects this massive leveraging of prior knowledge and, crucially, pre-existing, highly advanced infrastructure and tooling.
It really does. Which also explains why this rapid advancement wasn't just a solo effort by Saptarshi Das and Subir Ghosh working in isolation. The sources make it clear there was a broad team and significant institutional support behind this.
Yeah, you don't make this kind of leap without resources.
That kind of accelerated progress was only really possible because of dedicated specialized resources. A key piece of infrastructure mentioned was the 2D Crystal Consortium Materials Innovation Platform, or 2DCC MIP, which is based right there at Penn State.
Okay, what does a materials innovation platform like that actually do?
These MIPs are specifically funded, often by national science agencies, to accelerate the discovery, synthesis, and characterization of new materials with promising properties. The 2DCC MIP specifically focuses on providing researchers access to state-of-the-art facilities for growing high-quality 2D crystals, like the MOCVD reactors they needed, plus the advanced characterization tools we just talked about.
So it's like a shared high-tech workshop dedicated to making and understanding these 2D materials.
Exactly. It provides the essential, expensive infrastructure that individual research groups might not be able to afford or maintain on their own. It fosters collaboration.
And the funding, that also tells a story, doesn't it? It wasn't just one source.
No, it shows broad strategic interest. The project received funding from the U.S. National Science Foundation, NSF, which supports fundamental research.
Okay, standard science funding.
But also from the Army Research Office, ARO, and the Office of Naval Research, ONR.
Ah, defense-related funding agencies. Why would the Army and Navy be interested in 2D computers?
Well, think about the potential applications. Ultra-low power sensors for surveillance, lightweight and flexible electronics for soldiers or equipment, potentially radiation-hardened circuits. Maintaining technological superiority often hinges on pushing the boundaries of electronics, performance, miniaturization, and efficiency.
So overcoming the looming limits of silicon, finding that next platform, is seen as strategically important for national security as well as civilian technology.
It certainly seems so. This kind of broad support from both civilian science agencies and defense research offices signals a clear recognition at a national level that this is a critical area. Finding a path beyond silicon isn't just academically interesting, it's viewed as a priority.
It really paints a picture of a collaborative ecosystem, doesn't it?
Yeah.
You've got the academic ingenuity from DAS's team, the specialized high-tech infrastructure from the 2DCC MIP consortium, and the strategic funding from multiple federal agencies, all converging to tackle this really hard problem.
That's the model. And that collaborative model is likely a big part of why they were able to compress what might have traditionally taken decades of materials development into this much shorter, maybe decade-long focused effort to get to this silicon-free computer prototype.
Okay, let's try and crystallize the key takeaways from this deep dive for the listener. We started with the big problem. Silicon, our workhorse material for 80 years, is hitting fundamental physical limits as we try to shrink transistors further.
Right. Quantum tunneling leakage and short channel effects are starting to degrade performance, threatening the end of Moore's law as we know it.
The core insight from this Penn State work is the specific engineering solution they demonstrated. Instead of trying to fix silicon, they moved to a completely different platform.
A complementary duo of atomically thin 2B materials. They strategically chose molybdenum disulfide, MS2, because it works well as an N-type semiconductor.
And paired it with tungsten diselenide, WSE2, which they could reliably make function as the necessary P-type partner.
And crucially, they figured out how to grow these materials uniformly over large areas using MOCVD and integrate them, scaling up to over 2,000 transistors to build the first functioning silicon-free CMOS computer.
The implication here is potentially enormous, isn't it? This work demonstrates a viable, scalable pathway to potentially leapfrog the physical miniaturization limits that are boxing silicon in.
It really does. It promises a future where we could have electronic systems that are exponentially thinner, potentially faster eventually, and almost certainly much more energy efficient than what silicon can achieve at those ultimate scales.
And while this first prototype is admittedly slow, that 25 kilohertz number, the physics-based computational modeling they did confirms the potential. It shows that the platform, once fabrication is optimized over the coming years, could achieve state-of-the-art performance.
It's a genuine paradigm shift being signaled here. It proves that the fundamental logic of the integrated circuit, the bedrock of modern life, is not intrinsically tied to silicon forever. Other material systems can potentially take over.
Okay. Now, as we wrap up, we like to leave you, the listener, with a final provocative thought, something that maybe takes the core scientific achievement we've discussed and pushes the thinking towards a more foundational, maybe even philosophical level.
And this particular thought actually comes from the comment section on the original research paper in Nature. It was posed by a reader named Baohua Zhang, and it's a really insightful question that challenges the very language, the very definitions we're using as we enter this new era of atomic scale engineering.
What did Zhang ask?
Zhang essentially asks the researchers, and by extension asks all of us thinking about this to consider. When we talk about these 2D materials, are they really 2D?
What does that mean, really 2D?
Well, Zhang probes deeper. What is the fundamental operational difference between the concept of two-dimensional, as physicists use it to describe these materials, versus the concept of two-dimensional as a mathematician would define it? Okay. Like a perfect mathematical plane has zero thickness, right? It exists only in length and width. But these physical materials, even if they're only one atom thick, they still have a thickness. They exist in our 3D world.
Exactly. If the material were truly mathematically 2D, it would have fundamentally different properties. It probably wouldn't have a band gap in the same way, for instance. It wouldn't interact with the 3D substrate underneath it.
And Zhang's final question ties it together. Why, ultimately, can't physics be separated from mathematics in these discussions?
It's a brilliant point because it highlights how we often borrow precise mathematical concepts, like dimension, to describe physical realities that are inherently more complex and, well, messy.
That physical reality, the fact that the MOS2 layer does have a tiny thickness, that it does interact with the substrate below it, that it does have quantum mechanical properties tied to its finite size, that there might be tiny wrinkles or defects, all of that pushes back against the idealized mathematical definition of 2D. Precisely. And understanding that subtle but crucial difference, that inherent friction between the mathematical ideal and the physical reality, is absolutely key for the engineers who are now trying to control and manipulate these materials at the atomic scale. Solving the next generation of fabrication challenges will depend on mastering that messy physics, not just relying on the clean math.
So, as you hold your smartphone today, which is packed with silicon transistors measured in nanometers, think about this future where the active part of the transistor might literally be just a single layer of atoms.
MOS2 or WSE2, perhaps?
When we call that structure 2D, are we talking about a perfect, abstract mathematical plane? Or are we describing a tangible physical object that, despite being unbelievably thin, still possesses thickness, still has imperfections, and still has to obey the complex and sometimes counterintuitive laws of both classical and quantum physics in our three spatial dimensions?
Use that question, Zhang's question, as a starting point. Consider those foundational definitions of dimension and scale, because as this work shows, those definitions are no longer just abstract concepts. They are now literally shaping the future limits of the computing power that will be in your hand.
The silicon-free era might just be dawning. Thanks for taking this deep dive with us.